Hi, and welcome to today's webinar, where this is the first in a series of webinars we'll be running, looking at foam fractionation in the treatment and remediation of PFAS. My name's Connor Walsh. I'm the CEO of OPEC Systems. I'm joined today on the couch by Peter Murphy, the Managing Director of OPEC.
G'day guys.
And David Burns, the Chief Scientist.
Hi everybody.
Fantastic turnout, and what's really encouraging, very diverse turnout. So people representing government agencies, consultants, potentially some of our competitors, and that's good. That's what we want. We want to be engaged in conversation about how we can remediate some of the PFAS contaminated sites throughout the world. We want this to be quite an interactive webinar. So in the bottom right hand corner of your screen there's a chat box. We'd like you just to enter your questions in there, and at the end of the webinar we'll come back and answer as many of those questions as we can. We expect the webinar will take about 45 minutes, and at that point we'll come and answer those questions. So if you need to leave after 45 minutes, that's fine. We'll still publish we'll continue filming, and we'll publish the answers to that in that Q&A session online, so they'll be available to you. Just a quick overview of what we want to cover today. We will give just a bit of a background of PFAS. I'm sure everyone's familiar with PFAS, but we just want to make sure everyone's on the same page. We're going to look at existing solutions that are out there in the market at the moment. We'll give you an introduction to the remediation technology we've been working on, foam fractionation. We'll look at some of the advantages of foam fractionation, and then we'll come to that Q&A session at the end of the webinar. So without any further ado, gentlemen, what is PFAS?
Dave, you're the brains trust.
Thanks, Pete. Okay, so Connor, PFAS is basically the general name given to a very large group of compounds that partially or fully fluorinated, and they can have a functional head chemistry group. The subclass that we're interested in are the ones that have been used as firefighting foams, they've been used as surfactants, common consumer good products, and other specialty applications. Now basically the community has concerns for PFAS in these products, where they show persistence, bioaccumulative nature, and can be potentially toxic. So for example, if we put up on the screen PFOS, this is a typical compound under the PFAS family group name. This one has 8 carbons, it's shielded by a shroud of fluorine atoms, and it's the electron structure that gives and provides that shield that protects the carbon backbone. You can see here that this one has a sulfonated head to give it some extra functionality. That's typically what a common PFAS molecule looks like.
Sure.
And so what was PFAS used for?
Look, mate, it's pretty ubiquitous in the industrial landscape. It was used for, stain protection on carpets. It was used on clothing and shoes. It was certainly used for firefighting foam for many years, from sort of the late 60s, early 70s through to the 2000s. So quite a common man-made substance in that industrial environment.
So the area we're looking at is more along that firefighting training grounds and so on. But why was it so useful in firefighting training? What's it?
Well, as Dave sort of described, the fluorine atoms give it excellent heat resistance properties, and so it works well as it's heat resistant, and it made an excellent foam. So that combination of capabilities made it excellent.
So the foam is sort of starving the oxygen.
Absolutely.
And the heat. Okay, so it's killing 2 of those.
Yeah, like it worked extremely well. The challenge was
triangle.
The compounds persist in the environment.
Okay, well, yeah, okay, excellent. So why is it important then that we need, it's been around for a long time, so why is it important we need a solution to PFAS now? Why has it suddenly come up?
I suppose in recent years there's been a lot of, or an increasing amount of research, and particularly in the last few years an extraordinary amount of research into the area of PFAS. And Back in '09, it was listed on the Stockholm Convention as a persistent organic pollutant, the PFOS material. And so since then in particular, there's been a real focus on its impact in the environment, where it exists in the environment, a great deal of characterisation to see what sites it's on. And they're really under more of a precautionary principle than anything else, where we're doing the research to work out where it is and what impacts it's going to have in terms of human health and also environmental impact. So
if we go back to the firefighting training grounds, how has that become an environmental issue? So they firefight. Surely that's all contained on in the training area.
No, not really, mate. It's probably more the contrary, to be honest. So there's typically an apron environment where the firefighting training activities are conducted. The foam migrates off the apron, and then it's quite slippery, for want of a better word, and it migrates vertically down until it intercepts with the water columns, the aquifer, and then it'll the water table make its way down gradient, and there it sort of presents itself in various streams and rivers. It gets uptake by bore water and drinking water supplies, so it begins then to more and more interact with us and, and the broader food chain.
Okay. So what is foam fractionation?
Dave, you were the inventor of that one originally,
I guess
mate,
foam fractionation is a physical separation and concentration process that OPEC Systems has reinvented to rapidly remove PFAS and other co-contaminants that have high Henry's constants from water. And I guess we've also seen that it can also airlift other things that can be foamed out of solution. And I guess the key message that foam fractionation provides is that we've seen that it can remove 85% of bulk detectable PFAS from source zones, which includes 99% priority compounds, which are PFOS, PFHXS, PFOA, and other long chains.
So Dave, there's a graph, I believe, up on the screen at the moment. Just talk us through this graph with the...
Yeah, so this is an experiment that we did back in 2017 and repeated it many times in 2018 at pilot scale. So the graph on the left-hand side shows the common PFAS signature of 3M light water in contaminated groundwater. And we actually got this one from a defence base in Australia. So you can see the carboxylic acids and the sulfonates and a little bit of fluorotelomeres in that signature. And after about 35 minutes of aeration in our foam fractionation process, we've removed 85% of the bulk detectable PFAS, 99% of the key criteria compounds. And the ones that remain, they then flow on to be treated through our polishing stage, which is ion exchange. But if we go back to that last slide that was just up then, this slide shows the speed of the removal. So what we actually see there is that PFOS and PFOA is being removed to below the Australian drinking water criteria in about 3 to 5 minutes, and PFHXS around 12 minutes, and then some of the other shorter chains up to about 35 minutes, and what still remains in the water is removed by ion exchange resins as a polishing step.
So this is interesting. This is the infamous Experiment 45. So Pete, just talk us through a little bit of the journey as to how OPEC, one, got involved in PFAS, because I know as a company we're quite heavily involved in fairly technical remediation projects, unexploded ordnance, toxic remnants of war. We work in some fairly toxic environments in terms of managing fuel infrastructure and so forth. But remind me, how do we get involved in PFAS?
Thanks, Connor. Glad you asked. It's a journey that started about 4 years ago for us. So OPEC works quite a lot in the defence space. We put in big bulk fuel infrastructure. We remediate chemical weapon sites and unexploded ordnance, and so we work in that defence environment space a lot. And so when this problem came onto the defence landscape, well, probably 5 or 6 years ago now, we started to have some early conversations. And the way that OPEC has typically worked with these things is we look at the problem, we then internally kind of have a bit of a huddle, and so we got a team of 5 of our scientists together, and we sat down, we did a full literature review of all of the different technologies. And I mean, well, I'm sure the audience today is quite educated in PFAS and the compounds. At the time, we didn't even know what it stood for, I'd have to say, and so and there wasn't a lot of literature on it. There wasn't, certainly from a, you know, as an environmental contractor rather than a consultant, we were looking at remediation solutions. And so we went to the books, we hit the books to see what we could come up with. We ultimately came up with 5 different strategies for or technologies that we thought might be applicable for PFAS remediation. So they were oxidisation techniques, reduction techniques, sonication techniques. We looked at fungal digestion techniques, and then there was this outlier technology called foam fractionation. And we'd read a couple of papers, and frankly, they hadn't been very positive about the potential for foam fractionation to be used for PFAS removal. So we had almost discarded it as an opportunity, but Dave here, who was on the team, luckily had a strong background as a home aquarium hobbyist, and understood the principles of protein skimming, which is a very sort of parallel technology to what we're trying to do here. And so Dave pushed the argument that we should include that technology, and in hindsight, of course, we're very glad he did, because as the lab work began, so we took up a lab in the CSIRO labs down in Sydney, and we started conducting a series of experiments, and foam fractionation kind of emerged as the front runner. And I always like this image, because this is one of the very first experiments where we took some water from one of the defence sites and just got a little diffuser thing and pumped a little bit of air into it, and suddenly all these bubbles started to come out of the top of the flask. And so we obviously refined that process a little bit as time went by, and we started to construct various ways of bubbling and skimming the foam out. But the results, particularly that experiment 45, which, as you say, was quite infamous, was where we
infamous only because I think the budget extended to 50 experiments.
That's right. I mean, we'd invested a lot at this stage, and we'd had a team of guys working for nearly a year. So it was a great outcome for us to see those kind of results. And bearing in mind, in the Australian PFAS environment at the time, PFOS, PFOA and PFHXS were the criteria compounds that we had to deal with, and we were getting 100% removal of those compounds down to below detectable limits, down to the drinking water guidelines, just using foam fractionation alone. And so we had a mindset at the time that the only way you would really be able to achieve that was through resins and through some of these quite novel ion exchange resins and more traditional techniques like granular activated carbon. So for us to have a physical separation technique that worked to that level was super exciting.
Yeah, I remember it was a bit of a eureka moment.
Yeah, well, absolutely.
Lots of high-fiving going on. Well, we've touched on a couple of other technologies that are out there. Just we talked about ionised resin and GAC, granulated activated carbon. Can you guys talk me through a little bit more about what those technologies are and where we think foam fractionation might either complement those or fits into that sort of concept?
So I think foam fractionation is a technique, a physical separation technique and concentration process in the single step that can conserve the other processes of GAC and ion exchange resin and make those really shine by doing some heavy lifting at the front, so we conserve these valuable resources. There's less secondary waste to manage. It just makes sense that you would put foam fractionation at the front end of a treatment train followed by a polishing technique when you have to remove shorter chains.
Yeah, we've always taken a treatment train approach. Like even when we got those great results for the long chain compounds using foam fractionation, we knew then, and we still know now, that there are certain PFAS compounds that foam fractionation doesn't work on, and typically they're the sort of C1 to C3 and
Short
4
chain
range, the short chains.
Right.
You know, we get marginal results in that C4, 5 range. We'll get, say, 50% out, or possibly a bit better. But once we get to C6 and beyond, then we're getting really complete removal of those compounds. But while the criteria compounds at the moment, or at the time for us, were only the long chains, we always knew that any solution had to deal with the short chain issues as well. And so we've worked in collaboration with resin suppliers, and as you'll see in one of the videos we're presenting a bit later, we actually kind of scoured the world for a whole bunch of resin suppliers for PFAS specific resins to work with them, and they've been integrated into our plant up at the defence site Oakey job. So
would you say the big difference is that foam fractionation is a physical separation, whereas the other technologies are more, we absorb this, and is it as simple as that?
GAC is adsorption, and ion exchange is adsorption and ion exchange. So yeah,
different mechanisms, but I mean, typically in a historical sense, you would get the GAC for removal of the long chains and a little bit of the short, and then you'd use these specialised ion exchange resins for polishing and getting out the remaining short chains. We would posit that with the ability to remove 85, 86% of long chains at the front end of the process using a physical separation technique that requires nothing more than air bubbles into a column, it just makes perfect sense to optimise and the absorptive abilities and the ion exchange abilities of those subsequent materials by taking out the majority of it at the front end using physical separation. And that has some inherent advantages that we'll go through a bit later.
Yeah, okay. So we, you mentioned a little bit, Dave, with co-contaminants where there's PFAS, and I guess that makes sense. If you've used in a fire training area, you are going to have things like hydrocarbons that have been used as accelerants to get a fire going, and then. So how does foam fractionation deal with other co-contaminants?
So in the lab, we did a lot of sensitivity testing where we loaded up our full-scale pilot rigs with solids, like 50% solid. We aerated and evaluated how we still are able to remove PFAS, so the legacy priority compounds still work quite well.
What's a typical, yeah, I think we've got a photo of a typical water dam that
quite brown.
Yeah.
But the other things that the foam fractionator can remove are the high Henry constant chemicals like TCE, PCE, volatile hydrocarbons. That
suspended solids in.
Yeah. Volatile hydrocarbons could be avgas that you would expect to potentially be in a plume on an Air Force base. So foam fractionation, we think, is working very similar to an air stripper or an air stripper on steroids.
Yeah, and realistically for us, any solution, there was a few factors that kind of drove our design. So we're at our heart, we're an engineering company, so we wanted to develop a system that we knew, because of the quantum of the problem, that it had to be cost effective. So we wanted something that was relatively agricultural in the way it was built and put together, and the costs of operation had to be low. But we also wanted a system, because PFAS doesn't just neatly exist out there, unfortunately. It's always mixed with various co-contaminants. So we were really focused on a robust system that had the ability to deal with all of those.
And another quite interesting co-contaminant that we will try and put into an ARC grant study that we're starting with the University of New South Wales and Macquarie University here in Sydney is to see if we can airlift out microplastics out of the fractionator. Which,
big problem at the moment.
Which is a sort of a problem for water authorities who are finding PFAS and microplastics going through the sewage treatment works of the world.
Yeah.
And obviously these water authorities want to try and resell the biosolids as fertiliser farm amendments.
So just if I switch back to the viewers, please, if you've got questions, just go into the chat box on the bottom right hand corner of your screen, type the questions in, and as I say, we'll come back. I've got a little feed here, so we'll come back and we'll have that Q&A section. So please feel free to give us your feedback through some of those questions. So Pete, I know we've got a treatability lab down in Melbourne. Do you want to just talk us through a little bit about that?
Yeah, absolutely, mate. So in the early days, we set up obviously like most new technologies, we started at the lab scale where we build a lab down in Sydney, and as the results came in and we were getting more and more positive about it, we repurposed one of our laboratories down in Williamstown in Melbourne, and we dedicated that to PFAS research, and that lab's now been operating for 3 years, and it's kind of the hub of a lot of the work we do. So we do a lot of characterisation work down there, so water quality and chemistry changes from site to site. So what we wanted to do was have a...
Well, I think we can go down. I think
we'll go down there in a minute and I'll give you a full tour. But as water chemistry changes from site to site, we wanted to be able to take a client's particular water sample and then try and show what was the best treatment train to deal with that particular product. So if the viewers want to come with us, we'll just go down to Melbourne for something we filmed a little bit earlier. Forgive my look at the time, but we can take a tour of that plant.
So back in Sydney, we'd had some fantastic results from foam fractionation, and we were so confident that we thought it was time to take it to the next level. So we converted our Williamstown warehouse into a bespoke PFAS treatability laboratory. And in here, we've conducted, as I said earlier, over 70 discrete experiments to test every facet, every corner of foam fractionation, and trying to work out how to optimise it and make it work as efficiently as we possibly could. We were aiming for some very low drinking water criteria, and so we had to really optimise the process. And it was down here that we managed that process. There were 4 or 5 scientists working here at any given time, working on all of these different facets of experiments, and we were so happy with the results over time. We started with that little Butner flask, we built it up to the 10 litre protein skimmer, until finally some of the big boys that I'll show you around the corner in a second gave us the idea that we could actually commercialise this technology. So if you come around here, I'll just give you a quick look. Okay, hopefully not too noisy. We'd finished in Sydney with the desktop work, and we were super optimistic about the foam fractionation process and how well it was working. So we came down here to Melbourne to start to construct a number of different test rigs. We worked on about 8 different ones over the period we were down here, because there are a number of parameters that we really needed to test to optimise that fractionation process. But the obvious ones of column width and size had an influence. We wanted to look at the bubbles themselves, how they're introduced, what angle they're introduced, where they're introduced from, to optimise the process. We wanted to look at stratification within the system and understand where that PFAS was accumulating within the system. We wanted to look, really importantly, at the issue of co-contaminants, because PFAS doesn't exist in the environment in isolation, of course. It's out there. There's a number of different contaminants, everything from variations in water chemistry that impact nitrate and sulfate contents. We were looking at different colloidal soils and the impacts of clays in the process. And then probably most importantly, we looked at the impact of various types of hydrocarbons to the fractionation process, and whether the fractionator itself could manage those type of co-contaminants. Again, our confidence grew even further, and we started to ask ourselves, well, we've created this layer of foam, how are we going to extract it to create a hyperconcentrate? So we moved to an even bigger scala system. In these larger units, this particular one's a couple of thousand litres and moves us towards the sort of commercial scale we were looking for. We were able to put a lot of work into the design and construction of a really effective vacuum hood for extracting that PFAS foam at just the right moment, when it was just the right density, just the right weight of water in it, for us to really optimise the process and remove, right down to drinking water guidelines, the PFAS that was existing in there, the criteria compounds. Once we've gotten this engineering design to this stage, we handed it over to our design and engineering team up at our Brisbane office and asked them if they could start to look at how they could containerise and modularise these systems to get them ready for field applications, to get them out into the environment, out into the real world doing their job. And while our designers were busy doing that, the scientists down here at Williamstown turned their attention to the rest of the treatment train. We were looking at the pre-treatment issues and how we prepare the water for the process of fractionation and the subsequent polishing that occurs. And then the polishing itself, we were looking at various different types of polishing mediums, various types of absorbents, particularly ion exchange resins and how these would work for us. So if we come next door, I'll take you through some of the work we did there. With foam fractionation starting to get very refined, we were super happy with the process. We've been able to achieve brilliant results, much better than actually we'd ever expected with the larger fractionation units. So we were removing well in excess of 99% of the criteria PFAS compounds, which was just such a good result. The PFOS, the PFOA, the PFHXS, a longer chain, 6 carbon chain and longer PFAS compounds were stripping out a solution using the fractionation process. That was brilliant. Overall, of the entire suite of PFAS compounds that were in the processing water that we were dealing with from a number of different sites, we were removing on average about 86% of those. So we still had a small amount of PFAS to deal with. The fractionation had far and away done the heavy lifting, preserving things like the resins, but we wanted to be able to really get that out so that it wasn't just a drinking water criteria for those longer chain PFAS compounds. We wanted to remove everything that we found in our topper testing process. So to do that, we lean on some of these more conventional systems, the GAC and the resin, to deal with it. We went to resin suppliers from all over the world. We got samples in here. We did over 20 discrete experiments to test those against a range of different water chemistries. We tried them against a number of different co-contaminants just to see how they'd be impacted, how they'd be degraded, how their efficiency would be compromised, until we were really happy that we could go out into the field on these sites that we were dealing with and treat that water to the best possible standards. There were 16 stages in total that we developed for OPEC's water treatment plant for PFAS. 2 of those stages are foam fractionation, so you can imagine it's actually quite a complicated process to get right. But through the works we did here at Williamstown and the persistence of our team to look at every single facet of the water treatment process, we're now really happy with what we've got. We've got one of the first commercial, full-scale PFAS water treatment plants in the world, and we're also very confident that it'll work in a range of lithologies, in a range of different water chemistries, in a range of different environments all over the world. So couldn't be happier. We might head back to Belrose now. Hopefully you guys have got some questions for us, which we'd be happy to take and answer for you. So we'll see you up there.
Okay, so we're back here in Sydney, and mate, I'm very pleased to see your rugby injury there is healed up.
Hands better, bit of a shave.
Coming back. What I would like to do is in that video we talked about the vacuum head, and that's where a lot of our patents lie, and a lot of the magic happens. So I think we've got another video which just shows that in a little bit more close up, and maybe you want to talk us through that, Pete.
So here we've got the one of the heads in the mid-sized units that we were working on, and we've got a really healthy foam in that unit. We were you can see we're starting to crowd it into the top of the head. We move it up to the top where we've got a vacuum extraction system, and if you look carefully you can see that we've hit the sweet spot there. We're drawing off that PFAS enriched foam, which is then transferred to a knockout drum for where it quite quickly collapses, ready for the next stage in the treatment process. But the head is very much the sort of secret, so we call that our rapid phase. So once we get the first cut of the fractionate out of the processing water. We then put it into a hyper concentrator, and apply the rapid phase to it, the vacuum head capability, and that allows us to start doing some really strong concentration and extraction of the PFAS compounds. So.
It's good. We've got a lot of questions coming in, which is great, and one of them actually seems quite appropriate time to ask it now, so I'll ask it now. This is from Peter. What is the optimal bubble size and gas velocity for this process? Do the bubbles need to be very fine?
There's well, let me take a step back on that one. There is a range of bubbles that work optimally, and I guess that's part of our secret sauce. There's also the angle of injection is quite important, the hydrodynamic that you create inside the column. The height of the column is another important factor that we've been playing around with. So, yeah, look, the bubbles aren't quite as simple as just jamming them in through the Venturi system or a diffuser plate in the base. We've sort of come up with I guess, a balance that we think optimises the process, and certainly you can do it badly, as we did in many experiments where there was either too much veracity, not enough. The bubbles were too fine at times, and that didn't work. So we had to play around with that quite a bit.
I think another layer to add there is whether the aeration is too turbulent or there's not enough aeration to create the foam. So if it's too turbulent, we'll create so much foam instability that the foam will collapse and mix back down into the water column. Right. And in that instance, what happens is that we're not maximising the dewatering effect of the PFAS in the foam. Right. So what we're trying to do is remove a very dry, crisp foam that has the least amount of water in it as possible. So we actually want to remove foam that looks like a meringue.
Right. Okay.
That's the secret.
Okay. Well, we'll come back. There's a bunch of questions here, and we'll certainly come back to those at the end of the session. But I just thought that while we're talking bubbles, that was probably an appropriate time to put that in. So, guys, just let me ask you this. Well, what's the advantage then of foam fractionation over some of those other technologies we've discussed, say GAC and ionised resins and so forth? What's the advantage over foam fractionation?
Sure, mate. Well, I mean, maybe, we've got a table up at the moment that runs through some of the key ones, but I think what's important to point out is not just the advantages, of which we think there are a number, but also some of the disadvantages. So as we sort of alluded to, it doesn't work on short chains. It shouldn't be considered a technology for complete removal of short chain compounds. It works extraordinarily well on long chain compounds, and we'll get those down to below drinking water guidelines beyond detection limits at times. So it goes very well, but in that C1 to C4 range, there's mediocre performance. C4, C5, it gets a little bit better, but C6 and above it goes well. So it's important to know that when you're sort of putting it into context with these other technologies. Scalability, so they're sort of moving our way through these, like it's infinitely upscalable. I mean, if you imagine what we just saw down there at the Williamstown lab, but the size of a grain silo to treat huge volumes of water, that's entirely feasible. And there is no indication that scaling the process up has any impact on the efficacy of foam fractionation. In fact, to the contrary, Dave and I, after yesterday's presentation, were pouring through the results from OPEC, and those are 2,000 litre, 500 gallon vessels, of which we have 5 of those in a row that we'll see a little bit later, and those systems are getting it down to below the detectable limits for a lot of those longer chains. So it's quite a large system, and we think that's certainly we could get as big as we needed to.
But the other systems are all scalable as well.
Of course they are, yeah. So both GAC and resins can be scaled up to size. So that's great. That means they can all work contiguously to achieve a good outcome. One of the big advantages we think at the front end of the foam fractionation process is its ability to manage co-contaminants, and particularly hydrocarbons. Like for those, I'm sure a lot of people in the audience would understand the process of air stripping for removal of dissolved and hydrocarbon compounds out of solution. This operates in a very similar way. A lot of the contaminants, including some of the metals, will actually rise up with the the PFAS compounds and accumulate in that foam. So in that single mechanical physical separation phase, we're actually able to strip a lot of the contamination out. And I think that's fundamentally important, because one of the things that resins and carbon don't do well is they have a certain number of available sites for absorption and for removal of contaminants, and some of these resins are quite targeted towards being effective on PFAS. But if you flood them with hydrocarbons, if you flood them with some of the other co-contaminants, calcium carbonates and all sorts of things start to come into that solution, then you're going to compromise those resins. Those products are quite expensive. They create a large waste stream, and so
it's not that they're not as effective; they just become saturated.
Oh, they work really well. Don't get me wrong.
No, but with those co-contaminants, they become saturated early, or is that the issue with it?
Correct. So if you've got these contaminants, and even down to just suspended solids and even dissolved solids, they'll start to take up sites on the resin. Now, when you've got quite a lot of cost invested in your resin beds, and you've got a limited amount of bed volumes that they can handle, and you start to blind the top of those, you'll get channeling, you'll get all sorts of compromises to that. So we're able to strip that out early.
So foam fractionation is really a gross pollutant removal system, whereas resin and GAC are a lot more sensitive to water chemistry that's coming through it.
And I guess that then takes us to disposal as well. So I mean, you talked about Oakey before, which is obviously the plant we've got, the operating main commercial plant up in Queensland. Talk me through what the waste product is that's coming out of that plant.
Sure. So at Oakey, we produce, or we treat, I should say, 250,000 litres a day, which is about 66,000 litres for gallons, I should say. So it's not a huge plant, but it's a reasonable sized plant. But out of that 66,000 gallons, we're producing about 1 gallon of hyperconcentrate per day, so about 3.5 litres.
I think there should be a concentration slide that might come up on the screen in
a
moment.
And so this is a bit daunting when you first look at it, but effectively you've got 4 stages in our process up at Oakey that are the sort of growth stages. You've got the pre-treatment stage, you've got the foam fractionation phase in white, you've got the vacuum distillation phase in light blue, and then you've got the drum drying phase in dark blue. And corresponding to that on the right-hand side are each of the concentration steps for removing PFAS. So we're not removing any PFAS in the first stage, that pre-treatment, but in the SAF stage, there's 2 stages to the SAF. The first of them is the stratification mode, where we effectively are using a spillover weir design to remove a really wet, sloppy foam from the first cut. And in that phase, we'll typically get a concentration of about 20-fold. So we'll take the PFAS levels, for argument's sake, from 20 parts per billion up to 400 or 500 parts per billion in the first cut. We then take that hyperconcentrate, that wet foam, which goes to a knockout drum, and then when we get enough product accumulated in the knockout vessel, we run that to the next hyperconcentrator, which is another foam fractionation rig, but it's operating in rapid mode with the vacuum head incorporated that we saw a bit earlier. You'll get about a 50-time concentration step at that stage. So from our original 20 parts per billion, we go to 400 or 500 parts per billion. Now we go to 25,000 parts per billion, so we're getting more and more concentrated. As we step down into the light red phase, which is our vacuum distillation, we're removing, again, about a 30-fold increase. Typically, vacuum distillation takes out about 97% of free water, so we're left with about 3% by original volume. So again, what we had at 25,000 might be now 600,000 or 700,000 parts per billion. Then we go through a final drying phase where we desiccate the remaining liquor, and then we'll get it down, and that original waste stream might have gone from 20 parts per billion. It's now about 2.5 million parts per billion. So we've got these 4 concentration steps through the process that ultimately leave us with a very tiny volume of very highly concentrated PFAS liquor, along with a few other co-contaminants.
It's funny, if we just go back to that graph for 2 ticks, I love this when I understood it. and I love it because if you look on the left-hand side, that is essentially your water getting cleaner and cleaner and cleaner. And on the right-hand side, that is your concentrate,
your waste,
red, getting more and more concentrated. And as you go through those stages. So, as I say, when I first looked at it, I was like, oh, I don't quite understand it. Yeah. But once I worked my way through it, I went, wow, that is a really good graphical representation.
So up at Oakey, the plant's been running, it was commissioned on the 13th of May 2019 this year. So it's been running for a few months, and it's probably processed 6 million litres of water so far. And there's less than 100 mils of
100 litres.
100 litres of highly concentrated, low volume PFAS waste in an IBC. So it's probably going to take 2 years to have enough IBCs full of waste to put on a truck and send it for disposal.
Yeah, well, looking at that maths, if you're saying you've got 3 litres of concentrate coming out of every day, it's effectively after a year you've basically got a
gallon a day, 365 gallons a year, give or take, on that particular size plant. So, obviously we think that's a huge advantage when you're taking it. It sort of makes the waste disposal problem far less of a problem than it's traditionally been perceived as, because
you're not having to transport it off site. Well, sorry, fewer transports off site, and then a much cheaper.
For the audience's perspective, the concentration of PFAS in the groundwater that we're treating from deep extraction wells, it's about 10 micrograms per litre of total detectable PFAS, which includes about 0.5 ppb of PFOA, I think around just over 1 ppb of PFOS and 1.8 ppb of
With the second
PFHS.
webinar we cover, we're going to go into Oakey in far more detail, and I think we're actually going to go through, and because we'll have been tracking all that data, so let's hold some of that technical stuff for the. We don't want to give too much away. We want people to come to the second webinar. So any other? If we go back to that graph we had before, the other advantages, is it more power hungry or less power than some of the other treatments?
So one of the big benefits is that it's a low power consumption technology, and so you can sort of imagine. What we're doing with foam fractionation is just directing water through columns where we've introduced air. So there's very little resistance in the form of sorbent materials or absorbent or adsorbent materials that we're introducing. So there's less back pressure, so there's less energy in the process. And so we have energy monitors on each stage of the Oakey plant, and gradually we're building a body of data that's showing to us that for bang for buck in terms of, if ultimately we distill all this down to dollars per litre or per gallon treated, or perhaps dollars per gram of PFAS removed from the environment, then far and away the best bang for your buck comes from foam fractionation.
Right.
Yeah. And one of the reasons why we're able to use foam fractionation to reduce the C6 and above chemistries from water is because we're running the foam fractionator in this mode, so stratification and rapid mode, but it's also run in what we call continuous batch. So when you run in batch and we treat until we've removed down to a criteria, which in our case is a detection limit from the labs of 0.01 microgram per litre, we're able to do that. As opposed to running the fractionator in a flow-through process.
Yeah, so it operates a little bit like the plant itself operates a little bit like the pistons in a car. We've got 5 discrete 500-gallon reactor vessels, all fractionating for about 35-36 minutes a pop, and as one is emptying, the other's filling, and so we've got a continuous flow through our subsequent resin vessels, but we're treating in discrete batches in the fractionation process.
Yeah. So batch allows you to reach those Australian drinking water criteria of 0.07 micrograms per litre, but we actually get down to less than 0.01 micrograms per litre.
Yeah, and I mean on that site, actually our guidelines are about a third of the drinking water guidelines is the criteria we have to meet at Oakey, so it's quite stringent.
Right. All right. Well, the next question then would be, why would people consider OPEC systems?
Yeah, that's a fair question, and I think the answer to that is we've we've been around for 30 years. We're an engineering company. Engineering is what we do. So we build some huge fuel systems for defence, for bus, for train, the transport sectors. So we're used to pipes, valves, pumps, tanks. It's what's in our DNA. We also have a defence division that works in high risk areas. So we do chemical weapons. We do unexploded ordnance. We look after half of the marine oil spill stockpile for Australia. So we've got 8 workshops around the country. We've got offices in the UK. We've now got staff in the US. So we're starting to get a real, we've got a credible footprint. And as an engineering company, we can take these ideas, we can characterise the client's problem at our lab in Williamstown. We can design a water treatment plant that is
it's bespoke, really,
bespoke for that particular site. Yep. Yeah. And then we can produce and engineer that out of our workshops very quickly. We've had a real focus on containerising and modularising the systems so that they can be shipped to anywhere in the world, ready to plug and play. So effectively, you give us a dirty water stream, we'll plug into that, and we'll give you clean water out the other end, and you can decide what you want to do with it.
Yeah, it's a unique proposition in that it's modularised and ready to go fairly quickly, but it is bespoke for your particular site and the water that you're treating on that site. I think also from my perspective, we are a quality company. We've, as you say, Peter, we've been around for 30 years, but we've got our ISO 9001, we've got our ISO 14001, we've got AS 4801, which for our American audience is our occupational health and safety in Australia. Now that we've got branches in other countries, we'll look at extending that to the equivalent international standard. And those things aren't easy to get. They take a lot of time and effort to get and then to retain.
To maintain.
Yeah, that's it. Exactly right. So what we wanted to do now, I think most of the sort of questions that we wanted to just talk you guys through, we've covered. We want to go down. There's a little teaser video we've got of Oki, which is for the second webinar, and we'll send details to everyone who's attended this of that second webinar. But if we put that up, Pete, you might want to quickly talk us through what's going on at Oki.
I mean, the Oki site's, I guess, our flagship at the moment. It's one of the largest systems we've built. So you can see at the front, you've got the fractionator columns there, some of the pre-treatment and resin systems behind it. But effectively, that's a 67,000 gallon per day system that's doing this fractionation. So this is PFAS coming out of groundwater in the field there, and we're treating that to drinking water standards for discharge to the environment. We're also using that treated water for re-injection into the aquifer. We're also have actually partnered with a couple of the construction companies on site to provide water for dust suppression. So it's cleaned, it's ready to go back in the environment.
Completing the loop
close the loop there.
Loop. Yeah. So that's webinar 2. So we encourage you to when we send the invite out for that, we encourage you to join us there. We've got a bunch of questions here, which is great. So we're going to go through and start answering some of those. If you can't hang around for the Q&A section, that's fine, but we will make it available online so you can come back when you've got more time and look at it. But let's go to some of these questions now. If you've got more questions, we're here for as long as you
stick around as long as you need
to think. So I'll go through almost by as they've come in. So Rebecca has asked us, what detection limits are you able to get down to? And I suspect we've actually probably answered that. But
yeah, so the plant source water, so the feed water or contaminated water and our treated water is monitored weekly by an independent environmental consultant, which is WSP, and it's all overseen by the PMCA, which is GHD. But there's samples taken every Wednesday. The standard LOR is 0.01 microgram per litre. And then OPEC takes additional samples at its own cost, and we send that away pre-SAF, post-SAF, and other parts of the plant for trace level testing by Eurofins. And that's going down to 0.001, sometimes even lower to their super trace level. So we can really understand the granular removal of PFAS.
Okay, Rebecca, I hope that's answered your question. So Saraswati, I apologise if I haven't got that quite right, but
Good Australian accent there.
yeah. How does this work in an in-situ situation?
So in situ is where our journey began, actually. So we put the first couple of years into looking at how we could integrate this into recirculation wells below the ground. We've only done some very basic field trials. We've done a lot of modelling in the lab and sandbox work and so on to sort of work out the zones of influence. But I actually think it has enormous applications in terms of in situ treatment. We did some work at one of the defence sites where the initial concentrations in the groundwater, what were they?
Yes,
They were 640 parts per billion, I think, in that groundwater hotspot. Is that right?
Yes, we went to a defence base in 2016 and we custom made an aeration system with a vacuum head, and we dropped that down an existing AECOM groundwater monitoring well, the highest groundwater monitoring well on the site, airside. Had 640 micrograms per litre of PFOS in it, and after 30 minutes we'd removed 130,000 micrograms per litre of PFOS, and the resultant PFOS at the bottom of the groundwater annulus was 110. And the reason why it didn't go down to below drinking water criteria is that the groundwater table at that site is quite high. It's about 1.5 metres below the groundwater, the surface, and the recharge is really rapid. So as we're removing molecules of PFOS through the in-situ foam fractionation process, the environment's bringing us more molecules into the treatment well.
Gift that keeps on giving.
It's a gift, as opposed to a challenging confined aquifer.
Yeah, so that technology we call downhole foam fractionation, didn't we?
DFF, yep.
DFS.
And so that was actually our first patent. So we've patented all these processes, of course, and the downhole foam fractionation process was the first one that we moved ahead with. And so to the American audience, we are quite actively looking for field sites to trial downhole foam fractionation. At the moment, we've sort of gone more to a pump and treat approach, which, don't get me wrong, it works brilliantly. But if you can take that first cut from beneath the ground and you can get interconnecting downhole recirculation wells where you're effectively creating a subsurface barrier to stop migration off-site of PFAS contaminated groundwater, I just think it's a beautifully elegant solution.
Yeah. Well, you're not removing millions of gallons of water to the surface to store, test and re-inject or dispose anymore.
All happens in this quite neat cycle.
So Ron, I think you've asked the same question there. Have you attempted foam fractionation of PFAS in groundwater from in situ? Yes, we have, and I think we've covered it there. Brian has asked, based on your research, what factors affect the efficiency of PFAS removal using fractionation? How do co-contaminants affect performance of PFAS removal via fractionation?
Okay. So a little bit of that we've covered, Brian, but I mean, there's a number of variable parameters in terms of how well the fractionation works. So some of those are physical, so bubble size, bubble veracity, column width, column height, vacuum head pressure, the vacuum head height above the meniscus. Those factors are quite important. If there's any anti-foaming agents in some of the industrial processing waters we've worked with, then that can impact negatively the fractionation process. Dave, you got anything to add?
I think the one that caused us the most concern in the early days was the programming of the PLC logic to avoid getting surging in the aeration tank.
That's right.
So when the pumps would turn on and the aeration would turn on,
in there.
you get a bit of, initially we were getting a little bit of plumber's hammer and huge surging, which caused the foam to be wet and sloppy, or we would actually suck water up underneath the meniscus. So we'd done a few things. We put variable speed drives on the pumps. We reprogrammed the PLC logic controllers to avoid that surging.
Yeah.
And have we dealt with Brian's question on how do co-contaminants affect? Well, I think we have.
So we sort of did, but just to elaborate on that a bit, we really tried to break foam fractionation in the early days. Like we just threw soils and oils and various contaminants into the water streams to see. So we had a base sample of water with a certain concentration of PFAS, and then we would just introduce all these co-contaminants and see how our extraction efficacies were impacted. So we had 70 odd experiments that we did down there at Williamstown, and a lot of the focus on that was on co-contaminants. And as we sort of said before, and we sound a bit like a broken record if you talk to us for too long about it, but its ability to manage co-contaminants is actually the strength of foam fractionation as a front-end solution in a treatment train.
And it might just be, it's not so much foam fractionation is the issue, it's managing the polishing stages. So foam fractionation can, I guess, cause the precipitation of a few more things to oxidize and precipitate out. So you actually have to manage the post-foam fractionation process. So the extra aeration doesn't foul your resin or your GAC and resin. But it's easy to manage, but you have to do it.
Yeah. So Brian, hopefully that's answered your question. Peter, we've answered your question earlier today on the optimal bubble size. Amy asks, have you implemented this approach in high TDS waters? And if so, did you experience sludge solids generation?
A lot of the proving work we did with the groundwater wells had high TDS, and so in the next webinar we take you through the 16 stages that make up the Oki plant, and one of the very early stages is sediment management, and so we do settle out a lot of that sediment through basic holding tank design. We then also go on, we have plug flow reactors, we have an aeration tank, so we're stripping out iron and manganese and various other compounds. We've got a coalescing place separator in there, so we're removing free oils.
Multi-cyclone.
Multi-cyclone in there. We've got
bag filters.
Yeah.
So we don't really want suspended fine material even getting into the fractionator.
Yeah.
We want to remove that.
It doesn't impact the fractionator. The trouble is if it gets through to the resins, it does bugger the resins. So we just have to be a bit
just
careful.
take it out early.
Okay. Rebecca has asked, I'm assuming it's the same Rebecca, how does the technology differentiate itself from standard air sparge soil vapor extraction in situ?
Yeah. You can have a crack at it, Dave, or I'll do it. So
well, I think foam fractionation, we deliberately are trying to create a dry foam that sits on top of the water column above the meniscus. With air stripping, you don't really want a foam. And like, I guess traditionally everyone's trying to manage to avoid that. But typically a lot of people that run air strippers, they will actually see at foam if there's PFAS in the impacted water.
Yeah. I guess, Rebecca, the concept of introducing air bubbles into a column for removing a PFAS, of course, at that level it's quite similar to air stripping. I guess where a lot of our work has gone, as Dave alludes to, is how to manage, how to create the best foam at the surface, and then how to extract that. So the vacuum hood element of it is a differentiator, and it's been, that's been instrumental, I guess, in the success of the design.
Yeah, and we found that the having a water column, even compared to a DAF, the foam fractionation column removes PFAS below drinking water criteria in Australia. It's done very rapidly, and we get the biggest concentration steps or dewatering steps when we use a fractionation column.
We did We did actually originally kind of retrofit some old DAF systems and some air strippers because we thought, oh, well, you know, if these systems already exist on site. But unfortunately, if the way that the air bubbles are introduced and the size range of those air bubbles isn't within the right range, it doesn't work as well. It does work to some extent, but just not as well.
Okay. Nathan has asked, have you found a concentration threshold above which water will foam fractionate?
Yeah, we've sort of worked a bit on that. You're better on that than me, Dave.
We were able to foam potable water that doesn't have any PFAS in it, but the minute you de-energise the aeration venturis, like the wet foam collapses immediately. But typically, if you apply foam fractionation to impacted water, any PFAS concentration above 0.1 microgram per litre of total detectable PFAS, that's where it comes into being a real application to remove bulk PFAS and priority PFAS. I think if the total detectable PFAS in a legacy foam was significantly below 0.1, you possibly would just use GAC and resin or resin.
There's a law of diminishing returns where the energy that you invest in foam fractionation versus the additional cost of resins or protecting that resin bed, you know, balances out. And we think it's somewhere probably between 0.1 and 1 part per billion micrograms per litre.
And foam fractionation, like where its sweet spot is for legacy foam source zone remediation. So it's a no-brainer in that part of the site remediation process.
One of the interesting things we find is, so when you've got these source zones and you've got the legacy contamination in there, which incorporates a lot of the long chains, the short chains migrate and move more quickly than the long chains do. And so the further you go from the source zone, the less long chains you have in the signature, and as a consequence, the less relevance foam fractionation has in that application. So for us, we're trying to get in close to the source zones and do remediation where we've got high concentrations.
So relatively speaking, but so you would test and assess the site. If the concentrations are above 1 microgram per litre, definitely foam fractionation becomes a contender. To be put in a treatment train.
Okay, Nathan has also asked, what does our patent cover? And well, but you're the lawyer. You've
yeah. Look, I mean, jump in and have a look, Nathan. It's probably the easiest way to do it. But it sort of covers, as you know, the novel and inventive steps in what differentiate a patent, and so our patent covers the process of both downhole foam fractionation in the first patent and surface active foam fractionation in the second patent. It incorporates the vacuum head, it incorporates the means of injecting the air into the column and the hydrodynamics of the column that we create, and the treatment process itself.
As you say, probably best to jump online and
it's all there. Of course, you can have a squiz.
Yep. Jack has asked, can you comment on the effects of foam fractionation on PFAS precursors? Have we already...
we can cover that.
Have we covered that already?
So the precursors could also involve PFAS molecules that the labs aren't measuring. So we have done testing in our lab trials and our pilot treatability lab testing for TOPPER, the total oxidizable precursor assay. And I guess like what the results showed is that the foam fractionation system increases some TOPPER, but we believe that if we are creating more PFOS, PFOA, PFHXS and the longer chains, we'll remove those through the foam removal system. If there are still shorter chains, the GAC and or the resin will take them out in the polishing step.
But the short answer is it manages long chain precursors very effectively.
And then Jack again has asked, does PFAS concentration or pH have an effect on the process?
Yeah, so we're playing with that. And the short answer is yes, it does. Particularly post-fractionation, we've done some pH dosing both before and after the fractionation process just to get it, optimise it. It does have an impact. And the sweet spot for us is we want to be in a pH range. It wouldn't want to be any lower than 5.5, ideally no higher than 7, and probably more like 6.5.
Yeah.
Okay. Rebecca has come back with, besides suspended solids, what major water quality factors play into the efficiency of the system?
It's pretty robust, I'd have to say, in terms of water quality. Like, it can handle high levels of organics. Probably one of the...
Yeah. So up at Oakey, the water's really hard.
The calcium carbonate build-up is a risk that we've had to manage.
Yeah, so we've got to manage
that
the
again
water
comes
to
back to
scale.
that treatability lab, doesn't it?
Yeah.
Of actually, let's get some samples of your water in first, and let's look at what's going to be, what some of those impacts are going to be, and then design a system that's going to be.
Yeah, some sites are high in iron and manganese, so we've had to put in systems to precipitate that out in advance of the fractionation process.
Yeah. But I guess like at the end of the day, we take the advice of the resin supplier, whether it's Lanxess or Dow or Purolite. They provide some technical advice on how to manage the water quality chemistry, not for our SAF, but so we don't foul and lose pressure across each resin column in our polishing treatment stages.
Yep. Okay. And then Rebecca has, just jumping down, she's asked another question a bit further down. What air emissions do you have, if any?
So there's not a lot of air emissions in the system, but we have done a lot of testing for air emissions throughout the system. So one of the early things we did, I guess the human health impacts for us, for our staff, for people working on the site are probably the most important consideration in the whole equation. And so we've done baseline blood testing for everybody who's been working on the process, just to see where the starting point is for PFAS in blood. Then all of the systems where we've got the knockout drums accumulating, which aren't sealed, we've got carbon filters on those containers so that we're filtering any air out. But I'd have to say the testing that we've done shows that there is no notable volatilisation of PFAS compounds in the air adjacent to the units.
And any aerosols that might be created are plumbed back into the primary SAF vessels. So it's a closed loop.
Right.
And where there is a knockout drum, there's an exhaust that's connected to a carbon granulated carbon filter.
Okay, hopefully that answers your question. Rebecca, Peter's come back with, did the increasing in volume create a significant change in performance? And was there a change in the process as well, or was it purely an increase in the volume?
Yeah, that was a risk, Peter, that we worried about ourselves. Was it works beautifully in this little 10-litre Butner flask? How's it going to go in a 2,000-gallon tank? The reality is we did have to change some of the ways that the Venturis introduced the bubbles. Without sort of giving away too much, we're trying to create an optimal hydrodynamic inside the column that it's not too energetic to collapse foam, but it's sufficiently energetic to remove it. And so we have had to tweak the way that we introduce air, the height in the column that we introduce air at, the way that we get air into the centre of the column as the column gets broader. So there has been a little bit of mechanical engineering adaptation and change as we've upscaled. But as I mentioned earlier, Dave and I actually sat down after yesterday's presentation and went through some of the new Oakey results that had come through, and we are getting just using these large-scale fractionators, we're actually getting better results than we got when we were doing it in the lab. So that's been very encouraging.
So Zandong has asked, do we need to add any other chemicals in the liquid to help it foam?
So what we do, we just use air or aeration alone. Like you can add ozone and other chemicals, but we chose to stick with a simple foam fractionation process using air, so we didn't have to over-engineer with expensive corrosive resistant materials, which would double the capex of the plant.
Right, and the maintenance and all the rest of
the maintenance and the health and safety, which would feed into a more expensive OPEX. Typically, impacted PFAS waters will also include about 20 to 26% surfactant in the product, so that helps foaming as well as the PFAS in there. We did do a number of tests in the lab and in the pilot trials where we added a non-fluorinated surfactant, so a soap, to do multiple fractionations after the first fractionation process. So basically adding a soap as a surrogate to do a second and a third aeration to see how far we could actually drive down the treatment of the water in terms of detection limit.
Yeah, we're particularly looking at the capacity of amendments to enhance short chain improvements.
But we haven't had to do that up at Oakey because the plant is reaching 7 times below drinking water criteria without doing that. The plant actually has a really good application in Australia for treating trade waste that goes to sewer. So in that application, maybe we might add a little bit of fluorine-free surfactant to really drive that down lower and give clients an opportunity not to dispose to sewer, but to dispose to other alternatives.
Well, I think it's fair to say one of our challenges is there's a broad range of markets where we can potentially apply the technology, because PFAS is kind of popping up in sewage treatment, in landfill leachates, it's popping up in drinking water treatment, it's popping up in groundwater management, construction water management, and so we're trying to focus at the moment on working in hotspots adjacent to old fire training areas. That's where our focus has been until the last couple of months, and now with that plant commissioned and operating effectively and a really good reference point for us, we're now getting back into the lab, getting back into the research work and starting to focus on some of these questions around how we can further improve it, what other applications can we use it in, what other cross contaminants can we deal with. So that is a big part of the work. We've actually just had a call a couple of days ago to kick off 4 postdoctoral students who are starting work through the ARC program that we were granted, and a lot of those questions that we've got around how we can improve it are going to start to be answered over the coming months and years.
Yeah, and there's new derivatives of the solution that we're coming up with all the time, like the current solutions are all vertical columns, but we could remove PFAS in surface water as it flows through a horizontal design solution to remove PFAS in high flux zone applications at airports when surface water is flowing down a big dish drain and rapidly impacting a sensitive environment.
Think of a sort of a triple interceptor trap down at ground level or below ground level. As the overland flow passes down that culvert, we're putting it through a fractionation process and we're harvesting the foam as it comes up. I mean, on some of these culverts, you can get foam this deep that's flooding out, and so if we've got an inline in-situ system that's able to manage that, and so Dave and the engineering team have been working on some really cool designs.
Some of the places up, some of the airstrips up,
and we're quite interested.
The tropics there get deluged. Right.
We're quite interested if any of people in our American audience have field trial applications that would like to give that a go, like get in contact with us, please.
We've got a query from Mohammed. It's not so much a query, I think he's just asking us, are we aware of his company, which has been using volatilization and fractionation for many years, and in situ. All treatment is done below grade and you would not need to extract the water to the surface. I'm not sure. Not sure. We'll certainly come back to you. And
I think what we are finding is that the idea of using mechanical separation and air bubbles. There's some great mines in China working on it at the moment. I'm sure many great mines in America working on it as well as over here. I mean, I think one of the benefits Australia's had is that our Defence Department were quite early and proactive in trying to look at a solution for this. So we've had the luxury of some technology drivers allowing us to develop stuff.
Yeah. And then we got a question from Christopher, which I can probably answer, or we can. Is a calculated life cycle cost-benefit value for OKI available comparing the SAF to conventional PFAS removal techniques such as GAC and ionised redden? Not at the moment, but my understanding of what Defence are doing is looking at putting a number of these water treatment technologies into different sites, and that will be their sort of analysis of which one's going to be the most cost effective for them. So
yeah,
and we can do some lick your finger in the air calculations. We believe it's
Oh, let me jump in there, mate. Look, so the OKI trial's a 3-year trial, so we're collecting data daily, and so some of the data we collect is we're looking at the energy consumption. We're looking at the amount of consumables that we utilise in the process. We're looking at the labour that needs and is required to maintain and operate the plant. We're looking at the waste that gets generated from those plants, and effectively using those key parameters, as well as what did the plant cost to put in over how many thousands of gallons of water it's able to treat in that 3-year trial. We're slowly evolving the metrics of cost. We have firmly believed for some time that there's two things that ultimately all of us should want to find out. That is, what is the dollars per litre treated or per gallon treated, and what is the dollar per gram of PFAS removed from the environment. So a lot of the data we're collecting, a lot of the work we're doing is driving towards answering those really fundamental questions, because we're conscious that this problem is about treating trillions upon trillions of litres of contaminated water potentially. And so fractions of a cent are going to make enormous differences to the budgets of these projects. And so always since day one, we've been very focused on how do we do it in a way that is replicable, in a way that is cost effective, and in a way that is sort of achievable in a variety of environments.
So we'll have that data. It's just, I guess, and we'll be happy to share that. But after the 3 years,
it's evolving. It's taken time.
But,
we've got a couple.
What
of
we
months.
won't have is access to, say, the other
competitors,
water treatment plants that are up there. But Defence will, and that's what they'll be looking at, is what's going to be the most cost-effective solution for them in the long term. So we've got another question here from Saraswati again. What is your take on combining this technology with in-situ activated carbon treatment?
So we've looked at a few of them. I mean, Plume Stop's one that comes to mind, and a number of others. But in an in-situ application, this is an area that really interests Dave and I, because unfortunately it hasn't got a lot of traction in Australia yet. It's been much more pump and treat oriented, but we can imagine a funnel and gate approach, across hundreds upon hundreds of metres of intercepting contaminated groundwater, and adjacent to those gates we have consecutive arrays of downhole foam fractionation wells, which are operating collectively to take out the majority of PFAS from groundwater on its way through. But as we've said a number of times, it doesn't work particularly well on the short chains. So we can imagine a catch curtain behind our arrays that intercepts and locks up some of those short chains on the way through. Yeah. And that combines well with smouldering techniques that others have been developing. There's a number of ways. Like, the combination of technologies is definitely the answer there. We don't and never have thought that we're the one and only solution to the problem. We want to collaborate with other technology providers to try and provide the most efficient way of removing
efficient and cost effective.
Absolutely. We're certainly not too proud or too egotistical to try and work with anybody who's got an idea.
And then the other layer of solution that might be applied to that is the foam that we remove out of a in-situ foam fractionation treatment well could go for dewatering and then be connected to a chemical oxidation cell to destroy the foam waste at the site.
And the other thing that we're looking at OKI in particular is that soil washing, you know, obviously the majority of PFAS is actually bound to the soil. It's not in the groundwater itself. And so remediating PFAS contaminated soil is a big part of any future projects that we've got, that all of our countries are going to look at. And so most of those processes that I'm aware of are quite water heavy. And so treating PFAS contaminated soil is really about treating PFAS contaminated water, because you're going to rinse and wash that soil, and you're going to have contaminated water, and unless you've got an inordinate amount of water available for supply, you're probably going to recycle that, or certainly that water's got to be discharged somewhere, so you're going to have to treat it. So, you know, there's this integration of downhole systems, of soil treatment systems, of groundwater treatments, of above groundwater treatments that can all be part of one sort of elegant solution on sites.
Yeah. Excellent. Well, gentlemen, whether it's a good thing or a bad thing, I think we've come to the end of the questions. So I'd certainly like to take this opportunity now to say thank you to our viewers that have been watching this webinar. We hope it's been informative for you. You will get an email with a link to this webinar, so you can share it with colleagues who may or may not have been able to watch it. We'd also really appreciate if you can give us some feedback. This is new for us, and we're obviously trying to improve each webinar as we go along. So you'll get a short survey emailed to you probably today. Really appreciate if you can give us some feedback there, just so we can improve the quality of not only the webinar, but also the information that we're presenting and some of the answers that we're giving. So if you've got specific queries that you don't think we addressed in this webinar, and you'd like to come back to either myself, Dave, or Peter, we've got an email address which is enviro@opecsystems.com. So it's enviro@opecsystems.com. Feel free to drop us an email. We look forward to your company at the webinar too. Thank you very much, gentlemen. Thanks Peter.
Connor.
Thanks David.
Connor.
Thanks, Dave.
Bye, everybody.
Yeah, thanks, guys. Appreciate your time, and we'll talk to you next time for webinar 2. Thank you.
Thank you.